have a hard calculation simulation to do today. Everybody is okay? Are you ready? Your computer is running? Are you running? Good. So we will try to do a whole procedure today. Related calculation for strain hardening, and using exactly the same approach what I presented yesterday. So it has, you remember, 2 steps. One step is an empirical fit. It is just really a fitting. You cannot call it simulation. You cannot call it modeling. You know, there is a function which is invented, and it has 4 parameters. 3 of them you have to fit. One is just you take from the experiment, and then you get this function. And then from the function, which has parameters, we will use these parameters for a polycrystal plasticity simulation, and attempting again, but now this is really a simulation, using the VPSC polycrystal model to again obtain the experimental stress strain curve. Not only that, there is also more, but this exercise is part of a whole simulation process where you really model the mechanical behavior of a polycrystal. So of course, plenty of results are there coming out from the VPSC modeling. What can be, examined. Only one part is strain hardening, but it is the philosophy in this is that we get such strain hardening parameters if we can manage to match the experimental curve, that those parameters are general. They establish a general strain hardening theory, can be applied for any deformation mode. It is not only like tensor deformation. And you get a general strain hardening approach, and you can use it for anything. Even varying strain path, varying strain rate, all is possible. You can use it even in forming limit diagrams for any strain path. You can use it in material processing when you know what is this processing route. So this is the interest, really, to do that. You can even look into the texture which is coming out from the simulation. So that's why our exercise today is 2 parts. First part is just simple fitting. We are going to fit a strain hardening curve, which I think I put only this morning on. Do you have access to? Yeah, I do have access to it. So you too. You should download that curve, which is so. This is what you are looking at. These are the the files which belong to the hardening function fitting. Okay, if you download it, then these are the files you see. The experimental one is exp_curve_dat. That's what I would like to use. But it yesterday, when it was not the same one on in this file, So I would like that you check and you compare. If you have, I just plotted. If you have this in that file, you can plot it with Excel, for example, then this is what you should see. So I would like first you check it, that you have this file. This is an experimental measurement on copper. and copper and in tensor testing. This is why it is stopping, at 0.3 or so, because in tensor testing we cannot reach very high strain. So please make your Excel plot from that file. This is already something not very evident. I want to see the results. It's the same? No, it's not the same.
The values are different.
No. You have to download again only this file, experimental curve dot. This was the yesterday curve. This is yesterday curve. So you have to again download only the same file, same name. I think they still have access, no? So they are supposed to have access.
Yeah, I'll download. So I've already given to them, but probably for re-download, I'll again send them the email. And download it.
Sorry about this change, but it is more suitable. The file yesterday, finally I didn't know where it is coming from. You have it?
Yes, I have it.
Good job. So it has to be finished about 0.3, okay? It's a very nice strain hardening curve. Room temperature, tensile testing. Make sure you have the same. Don't have access to. Yes. And there was a link provided.
So where?
A link.
So where is this link provided?
He's providing. You are not on the list of the diffusion. Okay, ask him. I hope everybody got this Google Drive link, no? On which there are all the files. Submit. Yeah. Okay, so that's a Google Drive, my Drive. It's in my computer directly. Yeah, yes, is this one? If you want to plot with Excel, you have to remove the first 32.
You can share that with me.
This is it, yeah, very good. So that's the first point. Imagine that you are doing the experiment yourself and you are getting the result. It takes time, Experiment is taking more time than the simulation. In a way, it is easier to do.
data, different data.
It's different, yeah.
Yeah.
So download again.
Okay.
That will be new at the same place. You only need that file to replace.
This one also I have to delete.
Yeah, I don't need that.
This is also same.
This is still the same.
Still same.
Oh. Yeah, I think there's a small problem. My drive was not updated. No, it is okay. You can download. Actually, I did not update. Sorry. Experimental curve dot. This is on my Google Space. No, it is new. Check. It's coming? Is there? Okay. So I hope that you succeeded to get this. And now we are going to fit this function, I hope, perfectly with good precision. I don't recall the function exactly, no need. It is in the program. We only need to identify the parameters. The first parameter is the yield strength, yield stress. So this is the strain, and this is the stress. So at zero strain, we eliminated the elastic part, of the deformation already. It is just plastic strain. So you don't see this increasing, zero straight elastic part. You don't see. It begins at 55.3 megapascal. So this is the yield stress. This is already one of the parameters that we can read it from the experiment. This one, no need to fit. And then we go to the control file of this fitting program. It's a very simple program. You could do perhaps a better one. So the program control file is this one here, which is called Hardening control. You have also this one, yeah? Here we have to check the parameter range, what we are aiming. So I already put the initial flow stress. This is the first parameter, 55.298, yeah, this was it, megapascal, sigma 0. And then for the other three parameters, you see there are three lines which are defining an interval within which we are looking for the parameter value. So for this parameter h parameter, we define, it's also in megapascal, you know, from 10 megapascal to 100,000 megapascal. Why not? It's large enough to find something. It's important that it should be initially big, so that you know, not our solution is not outside. The second is the saturation stress in the stress strain curve. In this curve, we don't see the saturation stress. Yeah, so we cannot specify how much. We actually, from the function fitting, we will get it. So here, we know that our maximum stress was like 300 megapascal, yeah? So reasonably, if you put 2,000 maximum, that will be enough. We know that copper is never going to have 2 gigapascal saturation stress. Yeah? We know it. So it's reasonable to make this interval. Now, the other one, the last parameter, which is this exponent named A parameter, is more tricky. We have no idea how much it's going to be. So if you put from 0.1 up to 20. Now, the next option is to decide that these big intervals, which are initial intervals, how many segments you are going to divide. So let's divide into 100 segments, each of them. It means 100 times 100 times 100, 1 million possibility. But our computer is fast enough, we're doing, I hope, very fast. I mean, my computer is fast, perhaps yours even faster. Okay, the next parameter is the tolerance in precision, 1 megapascal. What does it mean? It means that if the average deviation, average, or perhaps the minimum, on each point, you know, from our predicted and measured one, should not deviate more than 1 megapascal. But if you have 300 megapascal and the only deviation is 1, if you plot it, you don't see the difference. So it's enough. 5, the next parameter will be maximum number of iterations. Because this is finally, you know, I mean, it's not really iteration because it is just calculation of values. This function which I defined, the deviation of, you know, all the data together. And it can do 5 times. It means that, and it is doing once, then it will be 100 times smaller, well-defined value. So with respect to your initial interval, your second guess will be 100 times better defined. And once it is done, then this very small interval will be divided again 100 times. So then it's already actually quite precise. But we set up maximum 5. You will see the iteration will inform you, you don't really need to do 5, but let's do 5. Already 2 or 3 should be enough. And then, finally, to check the result, what is coming out, here there is 2 instructions in the last line. In the output file, which will show your experimental curve and also the simulated curve, data file, they should be made so that you can immediately plot with Excel and compare the two. So this is convenient. So once it is all done and you set up your parameter file, make sure you have the same what I have here. I don't know if I can make it bigger. Oh yeah, look, bigger. Make sure that your control file is the same. You also make sure that your file, which contains the experimental data, is this one. It has exactly this shape. So that has to be on the top here 32. That's the number of lines. 32 data points. This should be the format. Okay? You have that too. And this is the first point we know. Okay, so I close this. And what we are going to do now is to execute this program, which is a simple program. If you are interested in Fortran programming, you open this file and look into. This is my creation. I like programming from 1971. You were not born. The language was, Fortran did not exist. So this is a nice program, not too complicated, because the process is not complicated. It's a kind of bracketing. It's called bracketing in Fortran. So it's reading, the parameters as you see, opening files, and then doing the job. So to execute this file, I have a special procedure. I will show you. So its name is hardening.exe. What I do, I execute in a DOS window. Do you know what is a DOS window? DOS. The DOS system was the first, preceding the Windows system, to do. It is still existing. It is inside the computer. It is useful for program running because if in Windows you execute a program, at the end it will be closed. And if there is any error message during the running, you cannot see because immediately program finished, window closes. So you can click on it if you want. It will do the job I show you. You click on this file, and yeah, it's beginning to calculate first iteration. But unfortunately, it will close. So I'm trying to stop it at number 3 here. Yes, I think it is now on hold. So you see here, Did you start the sign? Did you click? Anyway, I will explain you the DOS system after. It will be useful, especially for the VPSC calculation. That's why I would like that you learn it. Something new. As you follow the simulation, not simulation. Don't call it simulation. It's just fitting, okay? Oh, it's a good fitting. You will never see such a good fitting. So, iteration, H value, okay? Sigma sat, A, F mean it's the function which is defined to be as low as possible. If it is going to a very low value, then the fit is very good. And the last is average deviation of data point simulated and experimental. Average in megapascal. You see in the first step, average deviation was 0.6 megapascal already. But the function minimum is 20.47. And on this one, which the simulation is, the criteria is that if the F minimum is less than 1, then it's finishing. But I already accept the first one. Huh? And the third, after the second and third cycle, we have, you see the values are already converging. Both H, sigma sat A, and average deviation is very small decrease. It will never go to 0, you know. Of course, this is not really perfect. But already these values are pretty good. Now I let it continue. But it will be closed after the fifth. And I don't see the result. You see? You know that. This is Windows. So? Not running. Ah. It's not running. Then you must have a protection of execution file downloaded from internet. At all? Okay, let me see that. Did anybody succeed to run it? Yes, yes, yes. You don't have the same chance. Yeah.
Maybe actually this only we changed. These things we didn't change. What should I open?
It's just change the name. The tree, remove the tree. Xperf.net. And you see, you don't know why it is not running. I will show you the trick. It's a major problem in Windows system. And the program finished, it closes. You don't see any error message. But there is error message in Fortran. So to make it visible, I teach you a trick. We will work in DOS window. We will copy first the directory name. You put your cursor on the top and click once. Okay? You see it? That's the path. You put it into memory, Control C. Yeah? Control C. Is there. Now we open a DOS window. You go to Windows here. You type DOS. This operating system, that's DOS. That was before Windows, before 1989. So you choose this direct command. And the black window, what you see, is a DOS window. It's not going to be closed if the program is finished. Now, next thing. We are not at right position. You see the directory name is not the one where we want to be. We have to be in the directory which is here. You see here. My name, India, Roorkee, lectures, hardening, function fit. But we copied this, we put into memory. So we change the directory here inside, in the DOS window. To change the directory, you type cd, change directory, cd, and then the name of the new directory where you want to go. Luckily, it is in our memory. We put it into memory. So now you paste it. Just paste it. Yeah? Don't type, it's too long. And enter. Now we are there. So now the DOS window is in our working directory. And now we are operating as 30 years or 40 years before, okay? But it's useful. And you type the name of the program to run it. The name of the program is new hard. You don't need to put the exe. Without extension, the program will run. So that's the name of the program, and you make enter. No, it's hard new, yeah? Not new hard. Hard new. Right. And now you see the program begins to run. And what will be the difference? That it will not be closed when it is finished. If you did that if you did that like this, you would have seen what was the problem, because it would indicate you that one of the files is not existing, cannot find. But without doing this, you had no idea what happened. And you said, my program is wrong. Okay, so it's already finished and not closed. Did you understand the DOS system? It's 40 years old, not 50. 40 years old. But still very useful. And it is inside the computer. So you see now, we have 5 iterations, and we got the parameters. So the H value is 2006. Saturation stress. I go there. (335.7 megapascal). The exponent is 1.035, and this is just for information to see what is the precision of the approach. So we are done. We are done, but I leave this open. At the same time, the same thing to make sure that we do not lose. I put it into a file. It is here. It's an output file, permanent. It contains the same what we have just seen. And we're using the last line for, for the plotting. And actually, there is a file already prepared by the program, which says result dot, this one. So we open this one, and here you have the strain, the list of the strain values. Then first the experimental values are here, okay? And then the third one is the fitting, stress fit. You see, like, this one is perfect. The first one because the yield stress. The second one is already deviating a little bit. And so on. You see that, well, the values are pretty near. I think they are so near. If we make now an Excel plot, we won't see the difference. So let's do the Excel plot now. Use this file, the name is result dot, and plot the 3 first columns. I do the same. Better this way. Done. Okay. That's very good. This function is really like a miracle. You cannot make better. It's like one single line.
Yeah, yeah, very good. Yeah. Series 1 is
But
experimental.
this is measurement, you know.
Yes.
It's important. This is true stress, true strain.
True plasticity and true stress, that is the input.
True strain, you know, corrected for the section, you know, and it's not the engineering stress and strain. For that, it is not working. Has to be true stress, true strain. Very important.
You are also getting the rate of hardening as well as additional output.
Yeah, it is there. You can plot, but that should be plotted in the Cox Making Plot. You know, the rate, the function of stress. You can do. This is the Cox Making Plot.
Yeah.
The function, now you have to put here the stress, not the strain.
Okay.
The stress.
Sir, in the input file, we give like 1 ampere difference will be there, but in the last value, like 294 and 291,
Yeah.
means it's greater than 1, it will be there.
Yes.
Oh.
Not perfect. Just looks to be. Of course, this is not perfect, but this is a function which is the far best fit possible, actually, in strain hardening. There is no better with such a low number of parameters, like 3 parameters. Of course, you can have a polynomial fitting, for example. You take 50 coefficients, the polynomials you can describe. Even that would not be so good with polynomial fitting. And it has no good physical meaning. Here we have tau sat, the sigma sat, initial strand, everything. So very useful. And we will benefit from it immediately. To go into now polycrystal plasticity simulation. This job was, as I said, it's a couple of minutes. It's no big deal. But it has not much really, scientific value without using it for something. It could be useful for an engineer to make his calculation because it's an analytical function with low number of parameters. But we go further. You want to use the parameters in a VPSC modeling. So the next job will be, if everybody finished, anybody still working on it? It's possible. Yeah, check. Okay. So we have the parameter values. It is available in this file, which is called running. In the last, we choose, of course, the best values are here after 5 iterations. But starting from the third one, there is no change in the value. Now, for the VPSC simulation, we need the VPSC code. Did you download? Okay. Okay, so this is what you downloaded, VPSC Mets. And of course you see here many different programs and then files, but you only need to know a couple of them. The control file of the simulation, of course. And there is a main control file which is called SCTL, meaning self-consistent control file. This one. It's not too long, and we will examine the meaning of each line. For those who are not familiar VPSC polycrystal simulation. So the first line is the strain rate sensitivity, or for slip in the constitutive law, which is in 1 over m value, and for polycrystal plasticity simulations, we usually use the value of 10. It's not the real strain rate sensitivity of the material, but it is the strain rate sensitivity of slip for a dislocation. Sorry? I cannot hear because of this ventilation. You can come closer?
For any polycrystal system, we can use 10, the value 10.
Yes, yes. In general, we can use.
We can measure it by the experimental also, we can shoot it also.
If you put here a very low value, meaning like if you put 100, then the code is not sure it will be running, because the construction of the calculation implies a Newton-Raphson iteration process at 2 levels. And then if the yield function becomes very, very sharp, because you have such a low value of strain rate sensitivity, it concerns the shape of the yield surface. It becomes so sharp, and we are always at the edge. The process cannot work. In reality, the yield surface is not so sharp. It's very much rounded. And this value here, 10, also makes sure that the yield surface will be rounded. So 10 is a good value. The second value is the alpha parameter in the interaction equation. Yesterday I talked about it. It's an important parameter for FCC, BCC, cubic, for these materials like copper. 0.6 is a very good general value in the simulation. There was a whole study on it in 1994 when we introduced this parameter. It's a kind of tuning parameter of the self-consistent model. For different class of materials, it has different values. So for FCC, BCC about 0.6, but for hexagonal about 0.1 only, which will permit for hexagonal materials to have more heterogeneity in deformation. By increasing this value, we are going towards equalizing the deformation in different grains. If its value is like 10, it's like the Taylor model, homogeneous strain, almost. So 0.6 is a tuned value. You can make a citation to my paper in 1994 for that. Now, third line, type of hardening to use. In this version of this is the METS code, not the Los Alamos code, the METS VPSC code, using the same principles. I mean, Los Alamos is using the same because this was before. This was the first VPSC program made and then developed after. But I admit that, and my colleagues in Los Alamos, they are my friends. They did a very good job writing an excellent code. But that code knows other things. So this code here is using either no hardening if you put here 0, and there is no intrinsic hardening in the material. There can be texture hardening because grains rotate into harder positions. But, without hardening, we know that's so important in the material and especially in the viscoplastic self-consistent modeling that we had better do it. And this is the whole purpose today to do this exercise, to do a very good hardening simulation. So we have the second option is one, which is Bronkhorst-Kalidindi kind of hardening rule. Is the one which I presented yesterday, which was the inspiration for the macroscopic empirical approach, what we just did. So we are going to use this one for crystal plasticity in its original form. And finally, the option number 2 is called cell hardening. This is the model which I also presented yesterday, the dislocation cell-based hardening model. If we choose the number option 2 here, we have to fill out another file with the parameters for that modeling. We are not doing that, so we remain with the option number 1. Then, this matrix, what you see here, the diagonal matrix, it describes the initial general grain shapes of the population of grains. We will have 6,000 grain orientations in the simulation. 6,000. Each grain will be assumed to be equiaxed, meaning that in this matrix, this is a shaped matrix, we put 1 in the diagonal elements. It's like, in terms of interaction of the grain with the whole sample, it's like a spherical interaction. This shape tensor is changing automatically as you deform the material. So here in tension, it will be elongating the direction of tension. We will elongate in direction 1, the sample. And then this value will be like 2 here, and these other values will be smaller than 1. This ellipse. There will be no shear in this testing, so the other elements here will remain 0. They correspond to shape change when there is a shear deformation. So this is you have to check whether in your material the initial state of the shape of the grains is really, equiaxed or not. You might have a sample, but you start to make deformation already having initial shape, general shape. So then you have to fill out this shape tensor according to the geometry that you see. Elongated in direction 1, then here this is going to be larger than 1, and the other 2 will be smaller than 1. And you can put the aspect ratio according to your experiment. So that's the so-called shape tensor. Yeah?
So are we considering that the aspect ratio for all the cells are same, all the grains are same?
Yes, here we assume the same. This was the experiment. Behind there is an experiment, there is a microstructure study, there is even texture measurement on this material. So tensile testing and also texture measurement. Initial texture is measured, and I don't know it after it is measured or not, but the initial is important because we have to use the initial texture in the simulation. I will show how we use it. First, we just look at the general commands of the control of the VPSC modeling. So we are now in this line. This line is saying constant strain path, varying strain path. There are 2 options. Constant strain path means that your imposed deformation is always the same, it's just incrementally increasing. it's one direction. The variable strain path means that, your strain is during the time it's changing. You can have, like shear components which come, disappear, and so on. And if you have a good theory to describe that, then you can construct a velocity gradient file which describes how the strain is varying in time. It's a list of matrices. Each matrix is one state, deformation state. It's a gradient tensor, the velocity gradient tensor. For example, with a flow line approach of ECAP, which I also talked yesterday, one can develop that list, and then doing a simulation in VPSC for a very general deformation mode. But we are doing here constant tension. So the option is 1, constant strain path. And actually the strain itself is the velocity gradient tensor is here. That's very important to define clearly. So this is a second minus 1, velocity gradient tensor. The 1 here means that we are going to pull the material in direction 1 with 1 second minus 1 speed. Okay? And minus 0.5 here and also here means that it's becoming thinner in the perpendicular directions in an axis symmetric manner, because in direction 2 and direction 3, the two changes are the same. And it's important to check that here the diagonal is equal to 0. So 1 minus 0.5 minus 0.5, it has to be 0, because this code is only working in plasticity, not for elasticity. In elasticity, there can be volume change. In plasticity, there is no volume change, so then the diagonal is 0. There are no shear components in tensile testing, if you do it right. Because there would be, if you pull and then the axis is moving in one direction, you will have shear components. Now, you have to define how much would be the increment in one small increment of strain. The simulation is incremental. So you have to specify how much will be the strain increment in one step. If you do 32 steps, this is the next line here. So 32 times 0.01 is 0.32. It refers to, it says, strain increment in the maximum velocity gradient component. The maximum velocity gradient component is this one, the 1. Okay? So in direction 1, which we are pulling the material, our increment is 0.01 in one step, and we are doing 32 steps. We multiply the 2, and then we get that in this component, the strain will be 0.32 true strain. Okay? This is the calculation, small calculation you have to do to impose the right amount of total strain. Okay, now, next point is to define more parameters, like what kind of crystal structure you have. So 0 means cubic, 1 means hexagonal, and 2 means orthorhombic. And we are in a cubic for copper, so we put the 0 here. This line here specifies if you want to do Taylor kind of modeling, or self-consistent. The Taylor is included into the self-consistent. It's a special case. But we are going to do, of course, the self-consistent modeling. It is slower, but this is, belongs to all, like this parameter is a self-consistent parameter. And the grain shape is only calculated in the self-consistent mode. Now we go into the parameter values here. These tau sat, h0, and the exponent a, these three, but we just obtained in our previous exercise. We have to enter here, but it's not exactly the same. We have to do a transformation from the macroscopic level down to the microscopic one using the Taylor factor. But we don't know the Taylor factor. So we will do first just one increment calculation just to get the Taylor factor. So we will put here, instead of 32, we will just say just one increment in a first simulation. The Taylor factor will be appearing and that value is only needed. Then we come back to this file and we will specify these parameters here, okay? For one step, there is no strain hardening, not significant. Anyway, the important exercise is now first to get the Taylor factor. For finishing the file, let's continue. So next line is not relevant. Only the zero option should be used because this is a further feature of self-consistent modeling. We never use it actually, that it's able to make pairs of grains and then including kind of cluster effect. So one grain is allocated to other grains and then the effect of a cluster is calculated. We are not doing in general. But this is an option, and in long time it was looked at. Now there is here another parameter which is 300. It's needed in the stress strain behavior of the homogeneous equivalent medium, that sample itself. It's modulus value. We always put 300. And so far it was always working. But this is just initial guess. The code is finding the right value. Next one, shape parameter. Shape parameter means that if you put here yes, then the initial shape of a grain will change during the strain. The code is calculating, updating the shape. If you put the option 0 here, then the initial spherical shape is kept all over the deformation. But we know it is changing, so usually we put 1, unless we have a very strong reason not to change it, to let develop, Finally, here there is the 0. It's a so-called initial grain shape parameter. Because we define here in this matrix a general shape. If this is already done as spherical. But you can impose individual grain shapes. We will have 6,000 grain orientations here. Each grain can have different shape. If you have it from, for example, an EBSD measurement, such kind of distribution of shapes, you can put in. But for each grain, then you have to specify a whole tensor like this. And then its shape is given in a list, in a file. So here, if you put 1, then the program assumes that there is such a file in which each grain has different shape. And then it's not going to use the general shape, but going to use the individual shapes and working on that one. But we don't have it, so we put 0. Finally, the operating slip systems for this crystallography are given here with some more hardening parameters. So here we use the 12, 111, 011 type of slip systems, which is, the main general slip systems in FCC materials. There is 12 of them, and the list is given here. So this number 12 here means there will be 12. And the 0 in this line says total number of TW twinning systems. The code can do twinning simulation, but here we are not twinning, so this second option here is 0. Next number 1, total number of families. Family means one type of slip systems. Here we have only one, the 111, 110 type. So this option here is 1. And the last value here, total number of twinning families. There is not even 1, so it is 0. And then comes in this line the number of systems in family 1, 2, 3, and so on. We have only 1, and there is 12 in it. If I put a second value here, it will not count because it's only looking for one value. Yeah? 12. That specifies that family number 1 contains 12 slip systems. Now, next line, amount of shear in family I for twinning. As I said, no twinning considered in this simulation. So here, if you have twinning, you have to specify the twinning systems, and also you have to specify how much is the twinning shear in those systems. So this is 0 because we don't even have twinning. Then this line containing 4 parameters, these are those self and latent hardening parameter values, which I presented yesterday. You know, this 144 matrix, which is reduced to only 4 numbers, reduced to coplanar slip situation, collinear, perpendicular, and all the other cases. So this is self and latent hardening, and the values chosen here carefully, they are very reasonable values for FCC materials. You just adapt it. And then comes the list of the slip systems. So 12 line, and you know this is the slip plane, and this one is the slip direction within that plane. That you see here 2 numbers which are repeating. This is the critical stress in megapascal, which belongs to the slip system. Extremely important. Its initial value will determine how it will be the hardening later. And this value is actually which is controlled by the simulation. And our whole theory on strain hardening goes into this single parameter. This value is changed according to that hardening rule, which I had better show it for you again. Yesterday it was discussed, but here it is. This law here, you see, this one. Here, the Q, Cij values, you see. There is the H, tau sat A, and tau 0 I. That's what I talk about. We define its initial value. It will immediately define the initial flow stress. But this is a value at slip level and in many grains, you know. And the macroscopic value, we get it actually by doing a simulation, just one step. And we also get it this way, the Taylor factor. So this is actually the point of the whole business that we are doing since already now. Second day, to control fully the strain hardening. But this is a very general approach that I repeat, you can use after in any kind of strain mode. So, we have to set the initial value for tau 0 in this file. Here. Now, I put it 25.505, and you are wondering, how do I get that idea? Why it is 25.0.5 megapascal? Well, you know, I already did an exercise yesterday evening, so I repeated the simulation. So it's already set up with the right values, what you see here. I don't know if you have the same. I don't think you have the same as me. So you should copy already, you know, the values, otherwise your simulation will not be okay, especially I think these parameters here, but I will show you how to get them, okay? So this we have to set up, these Bronkhorst hardening parameters, and this value. It is twice because this is for dislocations. Dislocations can slip left or right. And this program permits to have different values, if you want, to slip for positive or negative. Well, because of this, you have to write it twice the same value because, we are not going to consider some kind of internal stresses, back stresses, whatever, which would make different stress in one direction than the other. So now the exercise will be, I will show you how to get the crystal plasticity hardening parameters from the empirical fitting function, what we did. Okay? So I go back to yesterday's presentation. And here, where we discussed how to do it. So there is this empirical one, in which sigma 0, 0 is the yield strength. You have to divide with the Taylor factor to get, for the crystal plasticity simulation, the tau 0 value. Tau 0 is shear stress. And the tau sat will be similar. The sigma sat value we divide by m. And for this rate of hardening h parameter, we have to divide with m squared. And the last parameter doesn't change. So this small exercise we have to do on the result what we obtained. So we have these 3 parameters or 4 parameters. So the result will be it was here. Yeah. So that was the simulation we just in the first part. And the H value empirical macroscopic is here. Sigma sat is here. And the A exponent is there. and the initial yield strength was no need for iteration to get it. So this is what we are going to divide. This is the h value. We have to divide with m square. The sigma sat we have to divide with m, and a we do not need to divide, just to put into the crystal plasticity parameters. But we need the Taylor factor. So now we need to do a simulation first, just one step, to get out the Taylor factor from the VPSC model for this tensile testing of our material. Our material is a copper, and for the VPSC model, what we need, I go to the VPSC space here in my computer. You have the same. It needs the orientation distribution of your initial material. It's not an easy exercise to get that, because you have to measure the texture of the material, with EBSD or with X-ray, and then you use a software to discretize it to a finite number of grain orientations. This job is already done. Of course, here we are not going to do the whole process, and the file is text-in.dat. This one. Text-in.dat. Text-in. I open. So this is our initial material. It's not random. We can study what kind of texture is in it, but the job was already done to get it in a discrete set of orientations. The number of orientations or grains will be 6,000. This is big enough. It's not small, not too big. Simulations nowadays with VPSC can be done up to 100,000 grain orientations, or even 1 million. But to describe with sufficient precision the texture, 6,000 grains usually is very much acceptable. So this file with 6,000 lines has the Euler angles, first three angles, Euler angles of the grains. And the last number is a relative volume fraction. It's like you can consider a micrometer cubic or something like that, but it's relative value. So this is a bigger grain you see, and this is a smaller grain here, because volume fraction is smaller, and here it is. It is coming from a very nice software how to get these relative values, so that not only the positions of the grains are well chosen, but also the volume fractions. The software name is ATEX. I'm opening right now. This one. This is made by my laboratory, and especially one of my PhD students. Benoit Bos here, you see his name. So this is a software which can be used for such purpose. Yes, good idea. Yes, we can continue on that. Thank you.